When the topic starts to heat up, interesting questions tend to emerge. One of them appeared recently among the channel's supporters. After all, how do you design a naval steam propulsion system? The question drew so much interest that it ended up becoming one of the most voted topics of the month. So today, we're going to walk through some of the main factors that must be considered when designing a naval propulsion system, especially within the historical context explored by this channel. The first point, perhaps the most basic, is simple in form but complex in practice. Are you actually going to use steam? That choice depends directly on the period in which the design is set. If we're talking about the early 19th century, the answer is already clear. Any attempt to create a fully functional steam propulsion system would be doomed to failure. Sail would remain the only viable option. But if we move forward in time, for example, to the 1930s, the situation changes completely. By then, there are real alternatives on the table. One of them is the diesel engine, which completely eliminates the need to produce steam. And that's where the first major technical dilemma appears. Diesel engines, when available, offer superior efficiency. With the same amount of fuel, they allow a ship to travel greater distances. However, their energy density is lower. In practical terms, this means that if you have a fixed internal volume allocated for propulsion, a diesel system will generally produce less total power than a steam system occupying the same space. So, if your primary objective is high speed, diesel may not be the best choice. On the other hand, if range and endurance are the priority, it becomes extremely attractive. But this decision cannot be made in isolation. In the early 20th century, fuel for steam systems, especially coal and fuel oil, was widely available in ports around the world. The same could not be said for diesel in large quantities. That reality led some navies to consider additional solutions, such as onboard fuel purification systems, similar to those used on certain experimental ships of the era. Naturally, this came with consequences: added weight, increased space requirements, and greater technical complexity. And the more space you dedicate to propulsion, the less remains for what truly defines a warship: armor, weapons, ammunition, supplies, and even crew accommodations. Every choice inside the hull is a compromise. If, despite all this, the goal is to maximize range with minimal fuel consumption, diesel may still make sense. There is also a hybrid solution: combined power plants. Some designs place diesel engines on central shafts and steam systems on outer shafts, attempting to combine economical cruising with high-speed capability when needed.
This approach, while ingenious, brings its own challenges. The machinery space becomes larger and heavier, two types of fuel must be carried, and engineering crews need to be trained on completely different systems. Logistics grow more complicated, and maintenance becomes more demanding. In the end, everything comes down to two fundamental questions: what can you sustain, and what do you want the ship to be capable of doing? Assuming the final decision is to use steam, either exclusively or partially, the next major question arises: what fuel will power that system? Up until roughly the first decade of the 20th century, the options were limited. Coal dominated completely. That meant large teams of stokers, exhausting physical labor, and constant refueling operations. It was a harsh reality. As the century progressed, mixed-firing boilers began to appear, capable of burning coal with oil sprayed in to intensify combustion and increase power output. By the 1910s, fuel oil became increasingly common, paving the way for cleaner, more efficient, and faster-to-operate propulsion systems. Interestingly, each type of fuel came with its own advantages and drawbacks. Although most navies transitioned to oil, history would later show, especially in the Japanese case during the 1930s and 40s, that this choice also carried significant strategic vulnerabilities. And it is precisely here that the full complexity of naval design truly begins to reveal itself.
Coal, even when it is not of particularly high quality, can be found in one form or another in most countries. It may not be ideal, it may require more effort to obtain, but it exists. The same cannot be said for oil. In much of the world, fuel oil is simply not available in significant quantities. This means that by choosing oil-fired systems, a country inevitably becomes dependent on external supplies. unless it happens to be blessed with natural oil fields or is large enough that such fields exist within its borders, reliance on foreign sources becomes unavoidable. And even in cases where oil is obtained through conquered territories or spheres of influence, there is still one unavoidable problem: getting that fuel back to the home country. And other nations, naturally, may have something to say about that. That said, once the issue of availability is set aside, oil offers extremely attractive advantages. In terms of energy per unit of mass, it clearly surpasses coal. Refueling is faster, cleaner, and far less physically demanding for the crew. By itself, this already represents an operational revolution. In addition, the use of oil eliminates the need for massive teams of stokers manually feeding furnaces. Although the ranks may still exist out of tradition or hierarchy, the reality changes completely. The image of hundreds of men spending entire shifts shoveling coal into boilers simply disappears from modern naval life. There is also a very practical advantage. When one fuel tank runs dry, supply can simply be switched to another tank. The fuel flows through pipes. With coal, the situation is very different. If a bunker is emptied, the fuel must be manually transported from another compartment, consuming time, effort, and coordination, especially during combat operations. However, these advantages must be balanced against broader strategic factors. First, the technological level of the country in question. Second, the security risks associated with dependence on foreign oil, something that, in practice, applied to most nations. And finally, cost. Fuel oil is more expensive than coal. This raises a fundamental question: is the additional performance truly necessary? If the ship being designed is not expected to operate at high speeds for long periods, such as certain escort vessels or auxiliary ships, coal may still be a viable solution, particularly if local reserves are abundant. It is true that this choice would become increasingly rare over time, but in specific scenarios, it still made sense. Countries with easy access to coal and extreme difficulty obtaining oil could resort to it, at least for smaller and less demanding designs. But let us assume that all of these issues have been resolved. Let us assume the project follows the most common choice of the 1920s, 30s, and 40s: an oil-fired steam propulsion system. From that point on, the next major technical decision emerges.
What type of engines will those boilers drive? In the 19th century, the options evolved gradually: trunk engines, compound engines, double compound engines. Each step brought gains in efficiency and complexity. But for the purposes of this discussion, the focus lies on the period from the late 1910s onward, when the range of available choices became significantly broader. One traditional option would be the use of vertical triple expansion engines. They are relatively simple to manufacture, do not require excessively advanced technology, and are well understood by the naval industry. They are not ideal for sustained operation at very high speeds, although the development of forced lubrication greatly mitigated this issue. On the other hand, these engines take up a great deal of space, generate considerable vibration, and are not particularly elegant from a mechanical standpoint. Still, they have one major advantage: they are cheap and reliable. Therefore, if a country faces industrial limitations, production bottlenecks, or budgetary constraints, this can be a perfectly rational choice, especially for ships that are not expected to be fast. Convoy escorts are once again a good example. But this is not the only option available. The next stage in the evolution of naval propulsion would lead to systems that are more modern, more efficient, and more complex: steam turbines. And that is where the decisions begin to truly become interesting. Steam turbines emerge as a relatively elegant solution.
They are not as simple to manufacture as vertical triple expansion engines, but they can still be produced on a large scale without requiring an extreme level of industrial capability. In direct comparison, they take up far less space, generate much less vibration, and eliminate the chaotic environment of oil, steam, and constant mechanical motion typical of traditional reciprocating engines. However, they introduce an important conceptual problem. Turbines operate best within a single rotational range, and when we talk about pure turbines, that optimal rotation speed is absurdly high, thousands of revolutions per minute. This is excellent for the turbine itself, but completely unsuitable for a naval propeller shaft. A propeller spinning at that speed would destroy itself almost instantly due to cavitation. In other words, the turbine is, at the same time, extremely efficient and deeply inefficient. It was precisely this paradox that led to a clear split in propulsion choices in the late 19-teens and early 1920s. This divide was particularly visible in the United States Navy, though it also appeared to a lesser extent in other navies. From that point onward, two major solutions began to compete for dominance: geared turbines and turboelectric systems. In the case of geared turbines, the problem of excessive rotational speed is solved through the use of a massive and extremely robust gear assembly. These gears reduce the turbine's rotation from thousands of RPM to a few dozen or a few hundred, values far more compatible with the safe and efficient operation of a naval propeller. This solution dramatically increases the overall efficiency of the system and, as a direct consequence, extends the ship's range for a given amount of fuel. However, despite this improvement, the fundamental issue remains. The turbine still has a specific rotational speed at which it performs best. At speeds outside that optimal range, efficiency drops. This can be mitigated by using multiple turbines, one optimized for economical cruising and another for high-speed operation, for example. Even so, there will always be intermediate speed ranges where the system does not operate at peak efficiency. This is where the more radical alternative enters the picture: turboelectric propulsion. At first glance, the turboelectric system appears contradictory. It is simultaneously more efficient and less efficient than a geared turbine. This is because it adds an extra step to the energy transfer process.
In this arrangement, the boilers still produce steam and the turbines still spin. However, instead of transmitting energy mechanically through gears to the shafts, these turbines draw electrical generators. Mechanical energy is converted into electrical energy, which is then sent to large electric motors responsible for turning the propeller shafts. The greatest advantage of this system lies in control. Regulating the amount of electrical power sent to the motors is fast, precise, and extremely flexible. Reversing direction, for example, becomes a trivial task. In addition, there is a natural redundancy. If one motor fails, power can be redirected to another with relative ease, something far more difficult to achieve in purely mechanical systems. On the other hand, there are unavoidable losses. Every energy conversion results in inefficiency. Perfect conductors do not exist, especially in the early 20th century. As a result, part of the energy is dissipated as heat at each additional stage. This means that at absolute peak efficiency, a turboelectric system delivers slightly less energy to the propeller shaft than a well-optimized geared turbine. However, that peak efficiency in a geared system only occurs at a very specific speed. In a turboelectric system, by contrast, the turbines can operate continuously at their ideal rotational speed, while the ship's speed is controlled solely by adjusting the electrical power sent to the motors.
In practical terms, if a geared turbine achieves maximum efficiency at one narrow point but performs only moderately elsewhere, while a turboelectric system maintains consistently high efficiency, the overall result can be fuel savings and greater operational range. That benefit, however, comes with another significant cost: volume and weight. Large generators and electric motors occupy substantial space and add considerable mass to the design. If a ship is not constrained by treaties or strict limitations, this issue can be addressed simply by increasing hull size. But when operating under international treaty limits, as was common in the 1920s and 1930s, or under tight budgetary restrictions, every ton and every cubic meter becomes critically important. And it is precisely at this point that the choice of propulsion system ceases to be merely a technical decision and becomes a political, strategic, and structural one.
Turboelectric systems, despite their conceptual advantages, come with a very concrete problem. Every additional square meter and every extra kilogram taken up by generators, motors, and cabling is space and weight that can no longer be used for armament, armor, or structural protection. On a warship, this trade-off is never trivial. At some point, a decision must be made as to whether operational efficiency truly compensates for the loss of offensive or defensive capability. But let us assume that you have chosen the most common path for the 1920s, 30s, and 40s, geared turbines. From there, we return to a point mentioned earlier, the use of multiple types of turbines within the same system. In a typical arrangement, the process begins with high-pressure turbines, which receive steam directly from the boilers. This steam arrives extremely energetic, spins the blades with maximum force, but it does not simply disappear afterward. After passing through the high-pressure turbine, the steam still carries a considerable amount of thermal energy. Sending it straight to the condensers would be wasteful. For this reason, most well-designed systems employ a low-pressure turbine, which makes use of this exhaust steam, extracting additional work before final condensation. The result is a real gain in efficiency. However, there is an unavoidable physical consequence. Low-pressure turbines must be larger. Their blades and rotors have significantly greater dimensions in order to handle the higher volume of lower energy steam. This choice by itself is rarely controversial, but the system can become even more complex. That leads to a practical question: how does the ship move in reverse? In theory, it would be possible to bring the main turbine to a complete stop and inject steam in the opposite direction, causing the blades to rotate the other way and consequently reversing the propeller shaft. This would eliminate the need for additional components. However, this solution requires the turbines to be fully slowed down before reversing, which is not quick, and it also forces them to operate in a direction for which they were not ideally designed. It works, but it is neither elegant nor reliable in all situations. The more common alternative is to install a dedicated reversing turbine. This is usually similar to the other turbines, but smaller, since full power is not required when moving astern. This turbine is arranged so that its rotation produces reverse motion on the shaft. In geared turbine systems, this allows the use of clutches. You disengage the gears connected to the ahead turbines and engage the reversing turbine to the propeller shaft. It is a clean, efficient, and reliable method, provided it is done at low speed. Attempting to engage or disengage gears at high rotational speed is an extremely expensive and destructive way to bring a ship to a stop.
And there is yet another type of turbine that may enter the equation, the cruising turbine. Ships rarely spend most of their time at maximum speed. On the contrary, the majority of their operational life is spent at moderate speeds. The problem is that main turbines, designed for high power output, become inefficient when operating far below their ideal rotational speed. One possible solution is to install a smaller cruising turbine. It still operates at high rotational speed, but produces less total power, delivering a more suitable output to the gearing system for economical speeds. This improves fuel consumption during long transits. Once again, the same trade-off appears: more weight, more occupied space in exchange for efficiency. Is it worth it? It depends. If the ship can cruise at economical speed using only part of its shafts, activating the others only when maximum speed is required, then a cruising turbine may be unnecessary. But if the operational profile involves long periods at intermediate speed with all shafts engaged, the cruising turbine may well be justified. These decisions are not universal. They depend on available space, permitted displacement, naval doctrine, and, most importantly, how the ship is expected to be used in practice. Finally, there is the question of the number of propeller shafts. Small ships, such as destroyers, typically use 2 shafts. Even smaller escorts may use only 1. Capital ships, on the other hand, usually adopt 3 or 4 shafts. Each choice brings direct implications. More shafts mean more turbine sets, more gearboxes, and more boilers. With 3 shafts, for example, you need 3 complete propulsion sets, but each can be larger and more powerful. With 4 shafts, the systems tend to be smaller individually, but greater in number. In addition, there are structural, survivability, and maneuverability considerations associated with each configuration. If a nation has extensive experience in building large-scale steam propulsion systems, it may be advantageous to opt for fewer shafts with larger machinery sets. Otherwise, distributing power across more systems can offer redundancy and flexibility. There is no single correct answer. Designing a naval propulsion system is not merely about choosing engines and boilers. It is about balancing efficiency, power, survivability, doctrine, and industrial limitations. And every decision, no matter how small it may seem, echoes throughout the entire ship.
On the other hand, if your naval industry is particularly skilled at producing smaller units but lacks extensive experience in manufacturing truly massive systems, then opting for a greater number of propeller shafts may be the more sensible choice. Even so, other considerations immediately come into play. One of them is how much power is being transmitted through each shaft. Because unless you are deliberately trying to create an underwater piece of modern art, sending several 100,000 shaft horsepower through a single shaft on a battleship is not a good idea, no matter how tempting it may look on paper. Continuing the analysis of a steam turbine system, another important decision arises. Will you include bypass systems? Some designs incorporate them, others do not. But what does that actually mean? Imagine that your high-pressure turbine takes a direct hit, loses blades, or suffers damage severe enough to render it inoperable. Without any alternative routing, that propulsion set is essentially lost. However, a single shaft may be connected to several turbines, cruising, high pressure, low pressure, and even reversing turbines. If no bypasses exist, the steam always follows a fixed path. If that path is interrupted at any critical point, the entire system shuts down. This is far from ideal, but it does have one clear advantage: reduced weight and structural simplicity. More sophisticated systems, however, include bypass valves and piping. If a specific turbine is damaged, that section can be isolated and the steam redirected along an alternate route, for example, sent directly to the low-pressure turbine. The result is not full power, but it is far better than losing the shaft entirely.
Some designs go even further, allowing steam to be redistributed between different boiler and turbine groups. Normally, each boiler group feeds a specific shaft, but with more complex bypass arrangements, steam can be transferred from one set to another. This can be extremely valuable in combat. Imagine a ship takes damage that destroys the turbine set of an outboard shaft while its boilers remain intact. At the same time, another hit disables the boilers of an inboard shaft while its turbines remain operational. Without bypasses, you would lose two shafts. With bypasses, steam can be redistributed and three shafts can remain in operation. In four-shaft designs, it is not always practical to interconnect every boiler group with every engine set. That would require an excessively complex network of piping running throughout the ship. A compromise solution is to allow connections only between adjacent units. This still provides a degree of compensation for damage without turning the hull into a labyrinth of pressurized steam lines. Of course, all of this comes at a cost. More piping means more weight, more occupied volume, greater maintenance complexity, and more penetrations through bulkheads, which can weaken compartmentalization and damage resistance. Once again, it is a delicate balance between survivability, efficiency, and simplicity. And speaking of boilers and their propulsion sets, another fundamental question arises. How will all of this be arranged inside the hull? At first glance, it may seem logical and even theoretically more efficient to group all boilers in one section of the ship and all turbines in another. On paper, this simplifies the layout and eases certain aspects of engineering, but like almost anything in naval architecture, this solution brings consequences that go far beyond thermal efficiency.
Everything may seem very organized and simple to execute until one not so small problem appears. If the ship suffers a direct hit to the boilers or the turbines, there's a very real possibility of losing almost all propulsion at once. And in a combat scenario, that is one of the worst situations imaginable. To address this risk, many designers turn to what is known as the unit system. Technically, this concept divides the boilers, or groups of boilers, and the turbines associated with a given shaft into independent sets. Each set is installed in its own compartments, separated by watertight bulkheads. This arrangement is then repeated for each propeller shaft of the ship. From there, designers gain flexibility in internal layout. One turbine might be positioned closer to the stern, while another, connected to an inner shaft, could be installed farther forward. The boilers can also be distributed along the length of the hull, breaking up the concentration of critical systems into a single block. The main advantage of this arrangement is clear. The loss of one compartment does not cripple the entire propulsion system. Even an extremely powerful hit is unlikely to destroy all boilers and all turbines at the same time. Some will be damaged, yes, but others will remain operational. And if the ship is equipped with bypass systems, maintaining movement after severe damage becomes entirely possible. The cost of this added survivability appears elsewhere. The unit system is less efficient in terms of internal space usage. It requires more room, more steam piping, more valves, and a more complex internal layout. Once again, we encounter the classic trade-off of naval architecture: weight and volume sacrificed in favor of redundancy and damage resistance. There is also an intermediate approach, which is not quite a full unit system, but follows the same logic. In this model, each shaft receives its own block containing both its boilers and its turbines, all grouped within a single large compartment. In a four-shaft ship, for example, there would be four large propulsion modules. Some designs adopt this solution because it offers greater survivability than placing all boilers in one area and all turbines in another, without the extreme weight and complexity of a fully fragmented unit system. Still, it has a clear disadvantage. If one of these modules is hit, that shaft is essentially lost. Unlike the more distributed system, the possibilities for steam redistribution are limited. With that, we arrive at the final two major decisions, at least within the scope of this analysis. The first concerns the boilers themselves. What pressure will they operate at, and what type of boiler will be used? By the 1930s and 1940s, designers had access to what were considered at the time low-pressure and high-pressure boilers. There is no absolute value defining these categories as they vary by historical period.
By the late 19th century, pressures of just a few dozen psi were already considered high, but by the Second World War, the situation was very different. Generally speaking, low-pressure boilers operated in the range of 300 to 350 psi, while high-pressure systems could reach 600 psi or more. At first glance, the choice seems obvious. Higher pressure means more power. But reality is more complex. High-pressure boilers require far more rigorous maintenance. Wear is greater, components operate under constant stress, and any failure becomes extremely dangerous. A leak at 600 psi is not just a technical issue, it is an immediate threat to the crew's lives. In addition, high-pressure boilers tend to be heavier, potentially less reliable, and require larger crews for operation and maintenance. Depending on how they're used, they may also consume more fuel. Lower-pressure systems, while less efficient in absolute terms, are more robust, easier to maintain, require fewer personnel, and have less catastrophic consequences when failures occur. This introduces yet another layer to the decision. It is not just about the weight and space of the boiler itself, but about the entire human system required to operate it. Crew size, technicians, redundancies, safety systems, all of these consume volume and displacement. There's also the industrial factor. High-pressure boilers represent the cutting edge of their era's technology. Is your country capable of manufacturing them consistently and reliably? Can it keep them operational under real wartime conditions? Or would these systems be so delicate that any damage, human error, or maintenance failure would cause a rapid collapse? In theory, many nations can produce high-pressure boilers. In practice, only a few can do so in a way that is reliable, safe, and sustainable. And here lies one of the most important lessons of naval engineering. Just because something is possible does not mean it is the best choice. If your industry, doctrine, and logistics can handle the additional risks, the benefits of high pressure are real. If not, choosing more conservative solutions may be the wiser decision. In the end, as with almost everything in naval architecture, the choice is yours, and every path demands its price. Another important point to consider in boiler design, especially when talking about navies such as the French in the late 1930s and early 1940s, is the type of circulation that will be adopted: natural circulation or forced circulation. Natural circulation boilers are the historical standard. Virtually every navy in the world relied on this system for decades. Their operation is simple and based on basic physical principles. Heated water becomes less dense and rises. Cooler water sinks to take its place. This cooler water is then heated, rises again, and at a certain point in the system turns into steam. The cycle continues, and steam is produced continuously. The problem is that this type of circulation imposes strict limitations on design. The layout of the piping must obey the natural laws governing the movement of water and steam. Bends cannot be too tight, and routing cannot be excessively compact. Otherwise, undesirable effects can appear, such as uneven pressure distribution, water hammer, and, in the worst case, serious structural failures, including explosions. Forced circulation boilers work differently. In this system, mechanical devices such as pumps, rotors, or impellers actively drive the movement of water inside the boiler.
This allows the fluid to travel through much more compact paths with tight bends and far more space-efficient internal arrangements. The result is significant. For the same volume or area, a forced circulation boiler can produce far more steam than a natural circulation boiler. This gives the designer two options: drastically reduce the size and weight of the propulsion plant, or keep similar dimensions and obtain much greater power, resulting in higher speed. The drawback, of course, lies in the dependence on these mechanical systems. If the forced circulation machinery fails, the boiler can lose functionality very quickly. This adds an extra layer of complexity, cost, and risk to the design. Even so, it is a technically attractive solution, and in certain contexts, an extremely advantageous one. We now arrive at the final element, the steam itself. At first glance, it may seem that everything has already been settled. Steam leaves the boilers, passes through the high-pressure turbines, then through the low-pressure turbines, possibly through cruising or reversing turbines, is condensed and returns to the system as feed water. The cycle repeats endlessly. And indeed, this is the basic operation.
But 20th century ships do not rely solely on their main engines. There are bilge pumps, lighting systems, electro-hydraulic motors, winches, elevators, auxiliary systems, and a vast array of other equipment that also require power. One option is to install dedicated generators, powered by diesel engines, or even small independent steam plants. But there is another, very logical alternative. Take advantage of the enormous energy potential of the main system and bleed off part of the steam to power these auxiliary systems. This approach has clear advantages. There is no need to carry additional types of fuel, there are no multiple combustion systems scattered throughout the ship, and, above all, these auxiliary systems gain access to an extremely powerful and reliable energy source. However, there is a cost. By using steam from the main system for auxiliary functions, you are diverting energy that could otherwise be used for propulsion. This means that if the ship needs to operate everything simultaneously while still reaching its designed top speed, the boilers will have to be larger than they would be in a system dedicated purely to propulsion. Additionally, if something happens to the boilers, you do not just lose propulsion, you also lose a large portion of the auxiliary systems precisely at the moment when pumps, electrical power, and internal control are most needed. Once again, the classic dilemma emerges: efficiency versus weight, cost, and redundancy. There is also a less frequently discussed but extremely important aspect. Steam engines, whether turbines or reciprocating engines, have a nominal rated power designed for continuous operation. However, this is not their absolute maximum power. There is always a margin above that rating where the system can operate for short periods. Using this reserve drastically shortens component lifespan and greatly increases the risk of serious failures. The higher the excess power demanded, the greater the wear and the greater the chance of catastrophic failure. Still, in critical situations, this extra capability can mean the difference between escape and destruction. How long that short term truly lasts depends on how hard the system is pushed and how well it has been maintained throughout its operational life. And, as with almost everything in naval engineering, this decision is not merely technical, it is strategic.
But why is all of this so relevant when we talk about a ship's auxiliary systems? The answer is simple. Speed requires steam, and steam comes from the boilers. If all auxiliary systems, heating, lighting, pumps, electrical generation, are powered by steam drawn from the main plant, that means the boilers are operating at a capacity greater than what is strictly necessary to drive the propulsion shafts alone. They are producing enough steam to supply the entire ship. And that creates an extremely interesting possibility. In an emergency situation, you can simply cut off the steam supply to those auxiliary systems. By doing so, all the steam that was previously distributed throughout the ship becomes available exclusively for the main turbines. The result is immediate. Far more power delivered to the engines and, consequently, a significant increase in speed. In practical terms, it is the classic absolute command: all steam to the engines. And this is not just theory. This exact principle was applied by the ship Carpathia during the rescue of the Titanic's survivors. The Carpathia operated its heating, lighting, and power systems through circuits connected to its main steam plant. When the crew realized the severity of the situation and the urgency of the rescue, they made an extreme decision. People on board were concentrated into just a few areas of the ship, only enough to keep them warm and provide basic lighting. Steam supply to the rest of the vessel was shut off. All that energy was redirected straight to the engines. The Carpathia sailed far beyond its normal cruising speed, pushing its machinery to the limit in order to reach the disaster site as quickly as possible. And it was precisely this decision that made the rescue of hundreds of survivors possible. Many of the people who escaped the Titanic disaster owe their lives to someone who, in that moment, had the clarity to order, "Shut everything down. All steam to the engines." It is a detail rarely explored in films and documentaries, but one that perfectly illustrates how engineering and design decisions can translate directly into lives saved. And with that, we reach the end of this overview. Throughout this video, we covered a substantial portion of the key factors that must be considered when designing a naval steam propulsion system. Naturally, this was a high-level survey. Each of these topics can be explored in far greater depth, and some of them have already been addressed in other videos on steam engines, turbines, and propulsion systems. If there is interest in exploring any of these points in more detail, just let me know in the comments. Suggestions and questions help guide future content. Thank you for staying with me until the end. I hope to see you again in another video soon. Until next time.